Because I remember looking at the computational neuroscience programming. Yeah. Maybe you can take that Maybe like. Sound. Yeah.
Okay. It seems that the spring has caused some issue with attendance, I think, right? But let's hope that we'll get some more customers as the lecture progresses. Okay. All right. Now, because of a political mistake happened 1,000 years ago, today is Good Friday for me. I have a religious commitment, and I have to get 10 minutes early from this class. Okay, so instead of 7:20, I will try to get out by 7:10. Okay, hope it's okay with you. It's not my fault. So the what I wanted to go through is I want to go through first some new items that showed up on the site, just in case you missed it. Kind of difficult to miss messages in Discord, but nevertheless, your final exam is now, the date is in Discord, says May. Okay, you missed it, May 8th. Okay, so this means like this is this and 3 more lectures and we are done. Okay. All right. So this is the reason why this study guide showed up. Okay. The study guide comes with some caveats that I would like to sort of outline. First, the scope of these questions may not be 100% overlapping with your scope. So I will see up until what lecture I'm able to sort of progress here to proceed and finish this lecture series. If I manage to finish reinforcement learning, then we do finish it. But if we don't, then we will stop at MDP. So that's my plan to finish it, which is basically the basis of reinforcement learning anyway. So my plan today is to finish the transformers and then enter the last representation that we are going to see in this course, which is the symbolic representation and some form of reasoning called logical reasoning. If I manage to get into logical reasoning, that's fine. I will do that tonight. But then I'll continue it and finish it off next week. And next week, I'm going to also finish, that's the plan, logical reasoning and task planning. This means classical planning without interactions, but staying at a task planning kind of level. And then the last 2 weeks, I'm planning to finish MTP and reinforcement learning. Okay. So that's the plan, which is a challenging plan because historically we never managed to finish reinforcement learning, but anyway, that's another story. Okay, so what happens now to the assignment 4? The assignment 4 is due in 2 days, right? And this is a very mild assignment. As I told you, who has finished it? Okay, a good chunk of you have finished the assignment 4. Did you get something out of it? Okay. All right. And then, of course, this brings us to the 800-pound gorilla in the room, which is the project. Okay. Who has started the project? Again? Okay. Two people started the project. Interesting. All right. Okay. So I think you only have effectively May 3rd is your deadline for the project, right? So we have, let's say the project is due literally in 3 weeks. Okay. The one ticket that I saw, for those who, obviously I know that one person started it, on that ticket is that, no function is executing. Okay, so One thing that you need to know is that the functions in the notebook are wrappers of API calls. In order for the API calls to be satisfied, then the backend has to be up, which means that the Docker containers have to be up, right? So the app with you, this means that the app with app now has to be brought up. Okay, so bring the application up so that the backend it runs, and therefore functions that you are calling in towards the backend are executed successfully out of that out of those notebooks. In case you want to look at what functions the notebooks are calling and bring the actual source code inside those notebooks instead of having wrappers and things like that, that's up to you. I'm not going to be involved in that. That's up to you if you prefer to do that route, but I think the project is well structured to satisfy all approaches. Okay, any questions on the project? Yes. Yeah, but I'm deaf. So, yeah. For the final, yes. Completely. I mean, from the beginning, when I say good morning to until good night. Good night and good luck, as some people are saying. Yeah. Yeah, that's right. Okay, let's see. Let's see. There is some people say, oh, why cumulative, blah, blah, and so on. You know, after the midterm are the most difficult parts of the course, right? So you really want to do it cumulative, right? To be even from the easier part of the course and to have everything from the difficult part of the course. That's the reason. Okay, so let's see. Today we are going to continue on LLMs. Okay, let's see. Let's move on now to what we have done earlier, ask some questions, and then move on into technical discussion. Today I have some doubts that today is lecture 11. I thought that today, the last time it was lecture 9. Last time it was lecture 9. And today is lecture 10. So lecture 9 kind of started with context-free representations. And if I ask you a question, why we call them context-free? What we built these representations, these dense vectors, why we call them context-free? Just one at a time, yes?
They don't know the previous words, they can only know that correctly.
They do not know the previous words. Well, the representation is for the specific token, okay? But yes?
They're independent of the context of the previous token.
Yeah, so previous one or next one. We window the next words, right, and the preceding kind of words in order to determine, if you like, the representation. But from that point onward, right, there is only one vector for the word bank. That's all you need to remember. One simple example to answer a question that you may face either in an exam or an interview or whatever. Okay, so there's only one and only one point in the d-dimensional space where bank as a token, if your tokenizer produced it, right, is going to occupy. Okay, and this bank will contain an averaging, right, of all the meanings of the term of the token bank. Either it's an institution or associated with crocodiles, as I said. Okay. Okay, so what we have developed effectively is a P-model, and we went through the development of this thing, and from first principles, maximum likelihood, we recognized that during the whole basis of this kind of development is a pretext task. The pretext task there was a prediction task, predicting the words that are around me. And if the prediction is successful, it means that the Z that starts the lifting process towards those predictions is the right one. Okay. Is the right one. That's the whole premise of that construction. And then we decided that we keep only one of the W star matrices, the first one, who is doing the projection, obviously, because we are after the Z. And because initially we had one hot encoded vectors, this ended up being a simple lookup towards that matrix that we can store and reuse. We can store it with metadata such as Wikipedia, English, whatever, and then we can retrieve it every time we want to have some kind of dense representation of those Wikipedia concepts. Okay. With the same tokenizing. Then we went through a very simple construction of a trivial kind of language model, which I need to repeat here. It's just basically a simple kind of RNN that it is gradually predicting. The only thing that is worth noting here is this P model here, which is basically predicting the next token given the previous tokens. And then when this prediction kind of happen, this token itself will enter now the context. Now we can start talking about context. For the E+1 to be predicted, and we call these models what? This type of models, we call them autoregressive. All right. Then we went to neural machine translation. Neural machine translation involved not only just the one neural network, but two, the encoder and the decoder. And this was basically a very straightforward implementation. I think I said that we are not going to do neural machine translation with transformers in this course, but I think you got the idea out of this kind of a simple construction. The formation of the thought vector that itself is changing as the training kind of goes by in order for the translation to be the right one. Okay. So then we have mentioned a couple of other things. We went through some kind of metrics. And finally, we entered the last kind of architecture we're going to see, at least in the neural network side, which is the transformer kind of architecture. And we started the discussion by suggesting that the transformers are devices which eliminate these recurrent connections that we had in RNNs, and therefore we can in parallel feed to them whatever input representations we want, the vectors. Right? Okay, and because we are feeding them in parallel, still we need to encode the position that every token has in the original kind of sequence, because now, because of the elimination of the recurrent kind of connections, we don't have form this hidden state with this input token, and then form the next hidden state with the next hidden token, and things like that. That information has to be encoded. How? We will encode it as this is the first token, this is the second token, this is the third token, and so on, massively parallelizing the feeding mechanism through the attention mechanism. And that is how we will do it, and we'll see examples of positional encoding later on. And then we have effectively the attention mechanism followed by some kind of a nonlinear kind of compute that it is being, we will call this transformer kind of block. And then we will have some body of blocks, one after another, followed by the head. That's the same general architecture we have seen before, but now we will focus on the first part here, which is the attention mechanism. Try to understand that. And we started the discussion last week. The discussion started with what we call the simple. Okay, so let me call this the simple attention mechanism, because there was going to be one final version, which is not this one. But nevertheless, the principles will be the same. So we wrote 3 sentences, and we recognize the fact that in these sentences, the same token, which is called bears over here, has 3 different meanings. And also we noticed that some other tokens in these 3 sentences are key tokens to extract that meaning out of bears. Okay, so You told me that love is one of the tokens for bears to be an animal. I love animals, right? So, but also I can love sports teams as well. So that doesn't mean anything, mainly, in any case here. But nevertheless, pain is going to be affecting quite strongly the bears as a meaning. And game is going to affect bears over here as a sports team. Okay, so that is a very intuitive kind of realization that some tokens are more important than others. And in this kind of attention mechanism we will build, we'll try to encode that information. Very simple, very straightforward. We'll encode this information as weights. So we will provide love with a large weight, pain with a large weight, of course, relative to the other weights which are in the context. So think about this axis now being the context, and three different contexts we have here. Three different contexts. Any questions on this? All right, so we said, okay, fine. Let's populate the context along the rows of this gigantic capital X matrix. And I say gigantic because the context sizes are pretty large today, right? But we will limit the discussion to just 3 tokens, okay? Or some kind of small number of tokens, just to write down the matrix explicitly. And then we have each vector over here is has columns, has a 4-dimensional representation. The dimensionality is monitor D of representations today. Transformers depends, of course, on the architecture, but some of them has thousands of dimensions, some architecture. And some of them have hundreds of dimensions. That's the ballpark of the dimensions we have in terms of small letter d. That's why I call this matrix a gigantic matrix, because in reality it's very, very large. Okay. But it's typically tall. All these tall matrices will have smaller number of columns than rows. All right, so we said, okay, fine. We will encode this information that some of this weight, weight information, and therefore I form the dot product of X transpose to form what is called the score matrix. The score matrix now is even larger than X because it's T by T, right? So in this kind of score matrix, I said, okay, I need to have relative weights between the the impact of the other token, let's say, towards, let's say, pairs. And I used a tool that I knew earlier, borrowed it from the heads that we have seen earlier from the various kind of neural networks called softmax. What softmax was doing? Softmax was a vector in, vector output function, right? Was taking in the vector of scores, right? And was producing weights which are between 0 and 1 for each one of them. So these are the weights that we call attention weights finally. And I told you, obviously these attention weights satisfy this equation because of the equation of the softmax expression. And I told you that if there is one graph, one diagram that you remember 6 months from today, that is it. Okay, out of attention. Attention is effectively, geometrically, the displacement of whatever input vector is coming in into the attention mechanism to a new location. If you remember that, that's all it's needed. The rest is mechanics. The attention mechanism we call self-attention because, as you probably noticed, the token itself is participating in this weighting mechanism, right? The bears, for example. Took the xi vector of bears and moved it now to an xi hat vector. And this xi hat vector is in a location that indicates to us that it is an animal. And these bears will, in the second context, will move to another location that, what was this other meaning? Tolerance, right? And the other location, sports team. Okay. One xi, 3 different locations. Okay. After this mechanism is done, we're going to have 3 different xi hats for bears. And the same thing will happen for love and game or whatever, right? All of these tokens will go into some neighborhoods in this d-dimensional space. Right now, this is a completely linear operation, and we will maintain the linearity until throughout. If you think about it, if you write this thing in a matrix form, in a vector form, if you vectorize everything, you have effectively implemented this thing. You took this is the S matrix here. You took the softmax, and this is the A matrix that you multiply with X to do this. For all tokens in your X matrix. So very straightforward things are happening. If you understand the geometric meaning of what we did, that's plenty here at this point. Okay, so are we ready now to move into the most difficult version of the attention mechanism by highlighting the limitations of this simple mechanism, which is also the key point to understand, because out of the whole transformer architecture, the next half an hour is really the whole meat, right? Okay, so let's start. Day is 4, 10, 26. Yeah, what? Oh, yes, this is this. Okay, let's see, transformer continue. Are you passing around the thing so I don't have to wait half an hour here until the end of the lecture? Yeah, pass it around so everyone is able to sign. Okay, okay, so let's see. Let me open my new set of notes, which I never printed. Hold on a second. What is that here? Maybe. Not paper. Not ability. Wait a second. Okay. All right. Okay, here we go. Okay. I have it now. All right, so we are writing. So the first limitation I want to mention, so this is basically the number 3. The evolved attention mechanism. Look at this X hat. Tell me, what was the contribution of the transformer in the context of X hat? And someone will say, we just got the X, because X hat is just completely a function of X, right? This X, the populating this kind of X can happen in many ways, okay? One way is to say, okay, I have this some kind of a dense vectors coming out of the context-free representation. And if this is the approach, someone can claim, hey, whatever someone else decided, right, to be those dense vectors, X hat is a deterministic relationship out of that mapping that someone else did. You can see it from the equation. X is involved here, and that's about it, right? So we would like to migrate now from this kind of deterministic mapping, right, to something that will have some probabilistic mapping. So in a very similar thing that we went, if you look at linear regression, we started with a linear model, and I gave you a whole bunch of basis functions that I told you this will be the good features, right? Featurization functions we can actually use, and moved into interpreting these methods as probabilistic methods, right? Ultimately, where the conditional mean was that linear model that we imposed initially. In a similar kind of fashion, we would like to go into introduce into the attention mechanism some statistical way where these attention weights will be determined. This arrow, the red arrow, in other words, will actually be determined out of, I will call it probabilistic version of nearest neighbors. Okay, we don't understand why right now, or what on earth did I just say, right? But this is what it will end up being. Some kind of a neighborhood will be built, but this neighborhood will be built in a probabilistic way. Okay. So let me write this down so we don't forget. Come on. All right. So we will write it down. Okay. So what I wrote here is up to this moment, the position of xi hat, let's say, is determined by the xi deterministically. And the other sort of thing that we said is to enhance the mechanism such that the xi hat location is a result of a statistical or/slash learnable these are the two things that we said. Okay. Now let's look at the second one. The second kind. Let's elaborate a little bit on the second kind of point. We were all along in this kind of course inventing sort of architectures, neural architectures that were handling correlations. Okay? I mean, we looked at convolutional neural networks as for spatial correlations. They were picking up spatial correlations from the, let's say, inputs. And here we are actually going to introduce this elaborate mechanism as an attempt to extract temporal correlations out of the sequences. Okay? And when I say correlations, I want you to think about correlations again in the same dot product way as we always been thinking about correlations. Dot product for us will remain as a mechanism in the more elaborate version of this attention mechanism. Okay? But it's going to introduce now the statistical properties. In other words, there will be something that will resemble PCA, something that will resemble PCA. These properties, in other words, will be extracted out of the data, and we'll see how this will happen by noticing the following. Let me write down the sentence again, just to clarify what I'm trying to say. I love bears. This is sentence number one. C bears the pain. This is sentence number two. And bears won the game. Now, bears here has some kind of a role, I want to call it, that is, syntactical or grammatical kind of role. Let me call this as the object of the sentence, which I hope you agree, that's an object. This is the verb. and this is the subject. In fact, we have seen some tasks in pre-processing in NLP that go and classify each of these tokens as verb, subject, adjective, and things like that. So in the second sentence, so let me, I think I used the orange for the first one. Okay. In the second sentence, what color did I use? Green and red. Okay, so in the second sentence, bears has the role of what? Verb. Okay. And in the third sentence has the role of subject. So I am posing the following kind of question. Is there any way that this mapping towards the right neighborhood, right, of the bears, right, in each of these three different kind of contexts can also be motivated by the role that each of these tokens has inside that kind of context? Okay, that's a question. And the answer, if we try to mechanize this kind of approach, I would suggest that, let me write it down though we don't miss the question. So I'm writing down that in natural languages, but not only natural, but in general in languages, the role, function of each token is highly correlated to its position in the linguistic patterns met in that language. So if we recognize that as true, which anyone follows what I just wrote, right? Okay. If we recognize this is true, then the question becomes how we can create, if you like, this kind of mechanism by the following. We want, via the parameterization of the attention mechanism. And parameterization should not be a foreigner term here because we always learn, we always pick up correlations via a set of parameters, right? We always were doing that. So we introduce some kind of parameterization in the attention kind of mechanism to convey the role that each token plays in the context. So if I am to imagine now, and this is a complete fictitious discussion just for us to understand, no one went and assigned these names to the axes that I will mention, but imagine a new coordinate system, a completely new coordinate system that someone wants to build. You are familiar with PCA, I suppose, to some degree. You remember principal component analysis? What was the job of PCA? Was to find a new coordinate system, right? Did we have this discussion in this class before? When I drew something, did I draw anything about that? Okay, let me just open a parenthesis here, just because I want you to use this kind of background into building this understanding of this new coordinate system. So if someone says to you that I have two features, x2 and x1, right? And I have these blue dots Remember these blues from linear regression? The blue dot data points. However, this is not a regression problem. Don't be confused by it. It looks the same, but there's no y here. There's no y here. There's no labels. It's just x1 and x2, right? And someone is telling you, hey, find a new coordinate system that I can represent the data. Okay. PCA was a linear operation that allowed you ultimately to suggest that, you know what, there is these two axes that are also good. I will call it coordinates. It's a new coordinate system that I can go and represent the data in that coordinate system as well. So then I was able to project these dots into this axis, project these dots into this other axis. And if someone asks me, well, since you have this new coordinate system, is it easier now to do some dimensionality reduction, right? Then in this kind of new coordinate system, PCA was saying, yes, it's trivial now to do some dimensionality reduction. Out of the two axes, which one would you keep? The orange one. And the intuition behind it, it is the orange, that was the whole premise of PCA, had carried in the projections all the data points. If we are to keep one dimension, this means that we have only one coordinate, not two coordinates now, right? If we are to keep one coordinate for each kind of data point, this is the axis we will actually form, and the projection will actually be the projections of these blue dots into that kind of axis, and this will have been a reduced kind of dimensionality data set, right? Which is now have just one feature, not two. Okay. And all of these things were actually happening, both finding this coordinate system, right? And of course, the operation of PCA, of course, was happening via a linear operation. A W matrix was involved, and this singular value decomposition was implementing this finding this axis. So there is some kind of a history in using linear operations to build new coordinate systems. That's all I'm getting at. And so this is just a PCA kind of background of principle, that is component analysis. A linear operation. So I'm suggesting now that I will try to find a new coordinate system whatever D of these axes will be in this new coordinate system, small letter d, where if I am to satisfy this kind of pattern, one of the axes will be an axis representing the objectness, another axis will be representing the verbness, another axis will be the subjectness, the adjectiveness, whatever. So I'm putting some names in this kind of axes, right? Although no one is doing that. No one went into PC and said, oh, this is like the sort of nice axis and the bad axis, right? I'm putting some names in order for us to understand the point of forming a new set of vectors out of X. Okay. So I'm going to do that. I'm going to write down the axes' names, and I will explain the rationale of that. Not objectiveness, it doesn't exist. Objectness axis. Let's say the verbness axis, then subjectness, and then the adjectiveness. So, and then I will imagine that, and this is what I'm going to draw right up I'm going to write below it. that I have some kind of a tokens in my context. Let's say I have this kind of 3 tokens. And each token, I want to imagine that it transmits 3 different vectors to its environment. Okay, so I will call the first vector, let's say the query vector, Q, the second vector, the key vector, and the third vector, the value vector. And I will do that for all of them. I will imagine that this basically is happening. They are sending messages. What a message is a vector. The message is just a vector, but they are sending them. And now I want you to look at the very first sentence. The very first sentence. You told me that Bears is going to, I mean, this thing over here, right? The lab is going to be quite impactful in the meaning of Bears. But if we are to implement this mechanism of some form of role-based, I will call it attention, role-based kind of attention, I can imagine that Bears will send the message as a key that I am an object. So the key sends the identity. Who am I? Am I an object? Am I a verb? Am I a subject? Who am I? Okay, so let me write it down. The key, this is the intuition, right? The key is identities. Who am I? The query now sends information. Who am I looking to find? Okay, so I'm asking to find someone, right? It's almost like in the older days there was a romantic advertisement. So if I'm 27, I'm looking to find 28, whatever. So the query is, who am I looking to find? So this is like a query. Who I look to find. Okay, not who, but rather what I'm looking to find. What? Okay, and so you can imagine that the Bears over here transmits the key. I'm an object, and also the query. I want to find a verb. I want to find a verb. I want to find something else. You know, like in this kind of context, I'm transmitting the key of a verb, and I want to find what is this thing? The object, right? And then here I'm transmitting the key of a subject, and I want to find another object, right? Which is what was that? I forgot. What was that? Yeah. This was the subject, right? So key. So the keys. So if I am to look at the first sentence, I'm going to draw an arrow now in this new coordinate system. I am going to draw an arrow that this thing is along the verbness axis. The first sentence is object, right? So if in the first sentence, this is basically the key Bears. I drew it orange because Bears is an object in the first sentence. So if there was a vector, it would be probably aligned along this objectness kind of axis. And at the same time, Bears is looking to find a verb, and therefore it will issue. Let me use another color, though it will not be consistent. The Q Bears will actually be along this axis. So what's going to happen now? All of these messages are going to find appropriate keys. All these queries are going to be responded by appropriate keys. Appropriate, who is going to determine the appropriateness of responding? The training mechanism, which means during training, queries that are going to be able to help keys that are going to be able to help the queries are going to start moving into the neighborhood of the query vectors. Why? Because in this neighborhood, if they are next to the query vectors, right, the dot product between those queries and keys are going to be maximum because they are in the neighborhood. If they're like in a 90 degrees angle, there will be nothing, right? But if they are in the neighborhood, if they move closer, and this is basically the statistical part of this thing. The training process, the stochastic gradient descent, is pushing these keys and queries into appropriate neighborhoods so they can respond to each other. And we are learning those neighborhoods and those responses from the temporal patterns that are present in my input data, which of course, temporal correlations, dot products. We are learning the dot products, in other words. So this is really the key aspect of this attention mechanism, right? The statistics is in the background, but the geometry, if you understand the geometry, then it's one and the same thing.
If you're moving the key, are you moving the key vector closer to the
All of everything is moving, right? So I will write down how the equations, and remember the PCA kind of analogy which I wrote down a bit earlier. Again, PCA is so if this linear operation here is the matrix, in other words, WQ and WK, forget about W for the moment, just W and WK. Like in PCA, are able to define a new coordinate system for the x's, right? In this coordinate system, the Q and the K vectors have new coordinates that are aligned themselves to the right role that they need to have in order for this attention to work, which means if the attention works, then the next token prediction will work. Think about the pretext task again, kind of thing. Because we are still in the representation learning part of the architecture, right? We are in the body now. We are inside the body. We are in building representations, right? So here's what's going to happen let me write it down. So in the d-dimensional space, let me draw the d-dimensional space like this. If there is some kind of coordinate system that has this query Qi and Kj, Kn, whatever, Km, I told you there's going to be some interaction between queries and keys. Those keys that are going to help this query will come next to it. Again, next is in this d-dimensional space next, right? You will now have the V vectors, which are in values out of another projection with a WV matrix, move to VI hat vectors via the enhanced, let me call it, . We are the enhanced self-attention. So we went effectively from X transpose. So we went from X transpose as a dot product to a query key transpose. All of the vectors present in the original kind of X matrix, now they have become a K matrix and have become query vectors, right, inside a Q, capital Q matrix. So writing down in the matrix form, that does not negate any of the previous kind of discussion. We just want to do everything like we did it with capital X. And so if I replace this by XWQ, which is basically the definition of the new coordinate system, and I have XWK transpose, then I'm going to have the product X WQ WK transpose X transpose. What changed? This. The WK WQ WK transpose. This is like known as a generalized dot product. This is it. So we went from a plain dot product to a generalized. So initially, the W matrices are obviously random. W matrices are random. Keys and queries are all over the place. If you visualize what's happening, the keys and the queries are coming together. The right keys are going to be around each query, so such that the task is successful with a good probability. What is the task? The task is always at the head of the net. So the V hats that I'm building, because these keys and queries are involved only in the red arrow, right? The V hats that I'm building about the actual representations that I'm feeding, if you like, to the head are going to be the right ones, obviously, if the red arrow is doing its job. Are you following what's happening? In broad terms, we are have baptized some kind of axes, right, in order to put our heads around why the key verb will show up next to the query verb that is looking for it. Yes, go ahead.
Can you clarify what the V vector is again? So you know,
The Q vector?
the V.
The V, okay. So the V, I didn't spend time on it, but effectively what the V is, think about it like a projection that I want to have a statistical way of defining this projection too. Now, in the same way as I had, if you like, the transformer itself, right, was defining the WQ and WK, in the same way it has to define also the WV. The V called values, right, the values are the actual representations which I need to deliver, right? So the key and the Qs are involved only in that red arrow, in the attention, in the dimension of the attention weights, that is, while the V's are the actual representations which I am building.
So it's similar to like the embeddings that we should.
Yes, it is similar to the events, but it's but it's a learnable embedding here, right? The value. So it will move. Condition, of course, on the attention weights. Condition on the red mechanism. Here. So if I am to draw a block diagram of this kind of whole process, I will start with capital X. Then I will have the first branch is going to be associated with a WQ projection to provide to me a Q matrix, which is E by D. The same thing will happen here with a capital K matrix, sorry, not capital K, but the WK, provide me the capital K matrix, which is still T by D. Then the dot product will happen to define the score matrix. And this score matrix will be T by T. Then there's going to be some division, which I'll explain, with 1 over square root of D. This is not R, but square root of D. Why there is a division, I'll explain. Then there's going to be a softmax, like we had earlier, to form finally the capital A matrix, which we had earlier. Obviously, the attention weights will actually move now, will be used to form the dot product between the values and the A. These are now the values, capital V of T by D. And this is basically the multiplication, as we have seen it earlier, which will give me the V hat is equal to AV. There are two things that are on the table right now. This we had earlier. The generalized dot product is here. We had the equivalent of X transpose. We had X times A here. So we have now, instead of X, we have V, let's say. This guy remains to be explained, why we have this division. And there is some kind of assumption behind this division. Okay, let me, I have some kind of notes here. So this softmax is kind of a, as you know, a kind of a sensitive device. So let me, so here I'm explaining now the scaling. By 1 over square root of D. So let's assume that the every query and key vector, and I'm saying now Q, comma V, K vector, because these are the ones that I'm interested in for the dot product, is distributed according to a normal distribution with zero mean and some kind of variance. And when I say normal, I mean to say every element of key and query vectors are normal. Let's assume that for the moment, right? Just to understand the basic assumption that behind this expression. So can someone tell me what will be the S then in terms of, which is basically the QI transpose where, and then it is the KJ, right? Let's say the ith and the query and the K and the jth kind of key. This will be, in terms of dot product, some summation will be involved here, right? From, let's say, n is equal to 1 to small letter d of qi, ki. Do you agree? This is basically a dot product, right? So I have some summation. So there is some kind of a, this is q. There's some kind of a expression with respect to the variance. So let's assume that we have independence. Assuming independence, between statistical independence now I'm talking about, right? Between, let's say, Q and K. What is the variance? The question for you is, what is the variance of S? What is the variance of S? So this has variance of the product of sigma to the power of 4. plus sigma to the power of 4 plus dot 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 plus sigma to the power of 4. These are how many terms? D terms. In other words, we have D sigma to the power of 4 as variance. So we see that as D increases, the variance of the dot product also increases. And this has some consequences on the behavior of the softmax function, first of all, with respect to the forward pass, right? If we have logits, in other words, at the input of the softmax function, right, that are pretty large values, what will be the effect of that? The behavior is listed in your website. And I think it's in the website. I need to move it, but right now it is under your single head attention discussion. If you go into single head attention, you will actually see here, let me convert this to, okay. Here's the behavior of the softmax. Come on. Really. What is the impact of that? If the softmax is really peaky, means the attention weights, some tokens has a really huge attention weight and while others have close to 0, means that a token does not receive any help from the others. And I don't want this. I want to have some balance, right, among the weights of the attention weight. So at least I let the machine kind of decide, right? So I want to have a situation such as this in the forward pass. Now, I can go into a discussion about the Jacobian and all this kind of stuff because I have in the back propagation of it, there's also a back propagation kind of impact. In the back propagation, if I have some really sparse, I will call it attention kind of weights, then the gradient, the downstream gradient flows towards the WQ and the WK matrices, which I need in order for them to adjust themselves, are becoming very, very small, the downstream gradients. I don't have that on the website yet, but there will be some kind of discussion about back propagation as well. So for these kind of reasons, I will suggest the following. If I go and divide by square root of D, right? If I go and divide, so the impact is peaky attention weights that result into a limited number of tokens to be involved in the red arrow. I hope you understand what the red arrow is. In the attention mechanism, right? Only a limited set of tokens will be involved because of these peaky attention kind of weights. And the second is basically in back propagation, diminishing gradients due to the Jacobian or i.e. downstream gradients towards the WQ and WK matrices that need adaptation. So by scaling with 1 over square root of d, I'm removing the d from the variance of S. And therefore, I maintain a much nicer, at least statistically, and this is, by the way, very important in the beginning, where everything is kind of random, and less important at the training, because after training, things are kind of evolving to the right place. And so by dividing by 1 over square root of d, then effectively this variance of S becomes sigma 4, sigma to the power of 4, and again, assuming independence. Yes, go ahead.
What's the word tokens to be?
Sorry, are you in A or B?
The A one.
A.
Tokens.
BT attention weights that result into a limited number of tokens to be involved in the red arrow. Attention. Diminishing gradients Q, the Jacobian, i.e. downstream gradients towards the WQ and WK matrices. Lots of stuff for just one scaling factor, but I thought, what again, it's okay. Yes.
I got the sheet done.
Yes, please. All right, now we go to this. Let's see. We have some idea about what we call now the single head self-attention mechanism. So I will enclose this into a box. And I am going to call it the single head. Because I'm going to use it now as a block itself to build what is called a multi-head self-attention mechanism. And also I'm going to introduce masking, which is obviously a needed thing for any decoder-based kind of transformer. Okay, so if we kind of follow more or less what's happening here, I want you to remember what we did also in CNNs when we looked at spatial correlations. We had an image. We were using multiple what? Filters to act at the same time throughout this kind of image. So think about the justification for the multiplicity of heads here as each head looks at various kind of temporal correlations, and at the same time, yet another head looks for some other temporal correlations. Okay, so think about it as capacity enhancement of the representation ability of the attention mechanism. In other words, we are going to have this kind of analogy in our mind to plot this new block diagram, which is not really new, but it just enhances the single head self-attention with more of the same. So we have single head self-attention that is being fed by just an X. So we have multiple heads and another, let's say, typically we have tens of these heads in an actual transformer, right? The representations that they are building, which are the V hats that I told you, they are concatenated. And finally, a mixing matrix. This is not a zero, that's an O. The WO matrix this WO matrix is D by D, produces the, I don't want to call the letter, but it is basically a T by D representation that so each of the, I'm not going to draw everything, but you can imagine that we have now dedicated to each head query, keys, and value kind of matrices to form the individual V-hats. Obviously, we do not want also to blow up the complexity. So if we have a number of heads, capital H, for example, over here, what we make sure is we do not increase the dimensionality here. So the concatenation will not increase it. So we divide with a number of heads to avoid increasing the V-hat. So the V-hat that we had with a single head attention or two heads attention or whatever remains the same in terms of D. That's called the multi-head self-attention. Each of these heads has its own kind of set of trainable parameters, which are the W, Q, WK, and WV matrices. I'm going to write here what I have as well here, that heads are working in parallel. To extract representations of the tokens across different grammatical, temporal in general patterns, and at the end concatenate these representations and let a WO matrix to weigh them. Because a mixing matrix is it's a weighting matrix, right? So
the rho is T cross D, which means that the weights for QH should be T cross D by H, right?
yes, it's D by D. The WO matrix.
Right, it would be D of mono cross
The D by D matrix.
the WO.
WO.
WO should be T cross D, right?
No. The WO, the output is T by D. Okay, let's calculate it. Each of these single head self-attention is it T by D or D by D? Is T by D. Okay, so it is T by D. However, we need to divide here with the number of heads, the capital H, right? So if H, let me define it here. Heads, this is the capital H, right? So I'm dividing D by capital H.
Yeah.
And this is another T by what? T by D divided by H and so on, right? So after concatenation, right, this guy is T by D.
Yes.
The after concatenation is T by D. Then I have the mixing, which is D by D. And then the output is T by D.
Yeah, the output is.
The number of hits is capital H. It's a parameter, architectural parameter. Well, guess what? I'm not done yet. We have some time to go to fully sort of close the loop in the attention mechanism, and then we'll see what is going to happen after that. So we need to do a couple of other things. We will take the multi-head self-attention. And first of all, we will preserve the ability in the attention mechanism of the transformer to backpropagate gradients, no matter if we have multiple of these guys stacked on top of each other. And we use another tool that we have seen many times before, which is the skip connection. So I don't think there's any sort of lack of any surprise by this. Okay, so we use that. We use this kind of capability. Where I think there's going to be some discussion is so let me call this what do I have here? Let me call this Z. It's capital Z, and let me call this kind of capital X. We use a term, a layer here called layer normalization. Okay. Did we talk about normalization in this class at all? Batch normalization? No. All right. So we will understand kind of layer normalization as effectively trying to implement what batch normalization is trying to implement. Okay. So we'll need to go back in time when we looked at sort of dense neural networks, right? Try to understand what batch normalization is trying to do, and then we will understand layer normalization as a kind of a constrained version of that. I'll explain the constraint. So let's try to understand now, to open a parenthesis. This parenthesis is batch normalization. I want you to go back in time when we looked at backpropagation. And during this discussion, I think, in this class, I'm not 150% sure, but there was a single neuron backpropagation exercise which I went through. Did I go through that backpropagation of a single neuron where I had a small dot product followed by a sigmoid, and then I was going through manually, and I was telling you something. Okay, so let's look at this example. Let me scroll in a fast way, not so fast. Around here, it is around here. I can sense it. Here it is. This was lecture 5. Wow, looks like that. 3 years ago. Yeah. Lecture 5. So there was the dot product followed by the sigmoid. This innocent example is going to help me introduce the intuition behind batch normalization. So I did the calculation. I was telling you what is your DW, right? I didn't have a loss per se, but you can imagine a loss, things like that, right? But I had this gradient of the y hat with respect to the weight W here, that goes into this dot product. And what was the outcome of this? This is the important thing. Proportional to X. Proportional to the input. Now, I want you to do some huge extrapolation now, okay? Almost miraculous extrapolation. Imagine instead of a single neuron now, we have a dense layer, right? Imagine that instead of a single neuron, we have a dense layer, and let's assume that the same thing happens, right? So now fast forward. And I have an X over here. I have layer 1 to form H1. Then I have layer 2 that forms H2. And then I have a head. Let's assume I have a Y hat on it. And remember, the gradient of the Y hat with respect to that W in that kind of single neuron is proportional to the input, okay? So if the gradient is proportional to the input with respect to the parameters of this kind of layer, there's going to be proportional to H1. The gradient that goes back is proportional to H1. Imagine how many layers, not only just two. Every single, in other words, layer has a back propagation kind of weight that it is associated with the input of the layer. This is the extrapolation I want. Right? So do we have, so what the kind of batch normalization is actually trying to do is to say, hold on a second. I believe that if this is the case, I believe with just a simple operation, I'm able to control, as far as I am concerned, the gradient flow backwards. And instead of leaving it to the chance of what layer 1 is doing, because H1 is controlled by L1 in the forward pass, right? That's how we get H1. But as we recognize, the back propagation through L2 is a proportion to H1. So I want to control H1. I want to control H1. What is a good set point for H1? I do not know. That's what back propagation is saying. I do not know, but I will introduce the scaling such that the scaling is learnable. How do I control the statistics of H1? Imagine H1 has a nice Gaussian distribution. How do I control where the Gaussian distribution will be? By its mean and its variance, right? So I'm going to introduce two trainable parameters, right? Two things. One is to control the mean and the other to control the variance. Okay. So I'm going to let the network decide, network will decide based on the performance of the Y hat, where H1 should be, where H2 should be, H3, H4, whatever, how many layers I have. So in order for you to understand batch normalization, you need to believe in this extrapolation, right, of what we saw in the single neuron, and then claim that there is a way to control the inputs of every layer, which of course affects, as we discussed, the gradients that flow in the backward pass. Okay, these are the two components that are needed. So I'm going to write some stuff down. So I am going to draw, let's say, two Gaussians for you to remember. Mu1, sigma 1 squared, mu2, sigma 2 squared. And these are going to be trainable parameters. And just to tell you also a little bit about where you will be able to find this, I think you will be able to find this in the neural network discussion in this kind of page. think about X being, if you like, normally kind of distributed, could be anywhere, right? And think about how you will be able to sort of standardize it, right, by putting it around zero. I need to estimate its mean, and I need also to estimate its variance, right, in order to implement this thing. Subtract the mean and divide by the standard deviation, right? So the estimation of this is happening across a single batch dimension. This is where it's called mu batch and sigma batch squared. Okay, so if I standardize it first, and then I can scale it with a trainable parameter, and I can offset it with another trainable parameter. Put it to everywhere I want. Standardize it, move it, scale it. That's it. That's what batch normalization is doing. So I took the Gaussian, I standardized it, and I moved it to the right place according to the network, and it's also scaled in terms of variance. There is some kind of discussion about the intuition over there, but I think it's not very difficult thing to understand what's happening with batch normalization. The problem that we have here, however, is the batch dimension in large transformer kind of architectures is not very large because of memory constraints. So we have, instead of doing this standardization across the batch dimension, we do it because we don't have many samples to do it across the batch dimension. We do it across the feature dimension, which is across D, the D dimension. And so it's almost like a transposition exercise of what we use in order for us to understand what will be the mu and the sigma squared in order for us to standardize it. Because if we have the batch dimension to be very small, right, then you understand the estimate for just one sample or two samples, so it's going to be very bad, right, our estimates, right? So the standardization step is not going to perform very well. So that is the layer normalization, and this is the reason actually we have it over here, is to help also backpropagation. Not only the skip connection is there, but also the layer normalization helps during training. Okay, so this is basically we have the first element, if you like, of the attention kind of mechanism. But we notice also that similar to our discussions that we had earlier, that everything here, because it's inside it, there's a single head self-attention. And if you see the block diagram of the single head self-attention, then it's a whole bunch of linear operations, right? We need to introduce, after that stage, some nonlinearity. Okay? And this nonlinearity is a multi-layer perceptron. It's implemented by a multi-layer perceptron. And the multi-layer perceptron accepts D dimensions, expands the dimensionality, lifts the D dimensions internally, and again projects back to D dimensions, right? So this is basically what the MLP will do. So there will be an MLP, which is itself preceded and by the usual tooling that we all now understand. Its environment also involves a skip connection and a layer normalization. And this MLP introduces nonlinearity in the learned representations. This is really truly where the V hat is. This is where truly the V hat is. So two blocks are involved in what we call the transformer layer. Block one, which is, I will call it capital A, and block B. So Z is actually over here. They are concatenated. So I will call that MTL. So I'll need to explain also the M, but I will write it down. Masked transformer layer. Is effectively the A plus B. So MTL. So I'm going to have multiple of these guys on top of each other. Of course, the number is a parameter that are typically in the tens. This is where my body is. Remember, I all started with capital X. This is the body. And then the transformer ends with the head, which is a linear matrix, W, let's call them W, and a softmax to give me my y-hat. This is where the head is. It takes all the representations. I'm having a V hat 1, passing through a V hat 2, and so on. As you probably intuitively kind of understand, most of the shifting by this kind of red arrow is going to be at the initial kind of layers, right? Subsequent layers will also be responsible for moving around these representations, but intuition says not to the as large degree as the initial layers of the transformer. So the body is going to be whatever representation it builds, delivers to the head, which is obviously going to take the representations, the T by D, and of course expand it to the V-dimensional space, right? Because it is really the V-dimensional space that we will find our next token, as we discussed earlier. The V-dimensional space is the vocabulary that the tokenizer built for us. So we will basically have a pretty sizable softmax over here. Trying to do the best token selection, the highest posterior probability of the next token. So in terms of the language modeling part, is the RNN in terms of the head, if you like. Nothing kind of changes. It is really this guy that is the main part. And the one thing I left on the table is the masking. That's what I left on the table, which I will not write the matrix because it's a bit involved for me to write. So I'm going to show it to you, this masking, which is a very straightforward kind of concept from the website. I'm going to go back to the large language models, and I'm going to go back to the single head self-attention. And the masking effectively means the following. During inference, do I have access to all future tokens? No, I don't have access to future tokens, right? So I cannot really seek help from future tokens to help me position myself in the D-dimensional space. I'm talking about, again, the attention kind of mechanism, right? So what we do with masking, the attention weights for those future tokens are becoming automatically zero with masking. That is, in a nutshell, masking. During training, obviously, I have access to, right, to the future tokens, but I cannot use them. That's why I mask them. So inference, obviously, I cannot use them. I do not know them, right? So, but in the training, I do not want to cheat. So I mask future tokens. How do I mask future tokens? I use the torch-inf whatever value there. I do not know what it maps, probably in the very large negative value, right? As a dot product. And then when this guy goes through a softmax, it becomes immediately zero. So when I'm in position one, I cannot seek help from these two guys, from these keys. Right? I cannot seek help from these keys. When I'm here, I cannot seek help from these keys and so on. So anything above the main diagonal becomes minus infinity. Yes.
This is only when we have to not cheat for like a decoder only.
Yeah, decoder only, yes. Of course, we have a variety of transformer architectures. We have decoder and encoder. We have cross attention and all the other blocks, which unfortunately we cannot really go through all the details, but I will leave you with, after I finish everything, I will leave you with a couple of references which I found to be a natural step for you to, during the summer, to follow through and kind of cover these kind of gaps that we're leaving on the table. So let's see. The next thing I want to mention and finish this kind of discussion is the last thing I left on the table is the position embedding. Okay, because we said that we need to encode that this is the first token, the second token, the third token, and so on. Of course, there are many positional embedding approaches today. And of course, we left also on the table sort of capabilities that we have to implement efficiently, efficient fine-tuning. We left on the table many things. That's why I will give you these references for you to at least see the Python code behind it, and the principles are pretty straightforward. But the embedding, the positional kind of embedding is definitely something I want to cover because it's part of the kind of mainstream story. So let me write it down as it's called position embedding. Even in position embedding, there is absolute position embedding, relative position embedding. I'm going to be dealing with the original positional embedding approach that it was in the original paper in 2017. That is kind of difficult to kind of understand when you can come across this kind of sinusoidal and cosinusoidal kind of functions. And the rest of the approach is much, much easier to understand. For example, there is an approach that is actually being used extensively today that does not involve these functions, which I'm going to explain, but it involves some kind of a learnable positional embedding layer. But the principle is the same. So first principles is how do we encode position? And I will use a tilde to denote the token after the incorporation of the positional information, which is surprisingly not a concatenation operation, but an addition operation. This itself is surprising because if you ask me, okay, what will be the most straightforward way to encode position information? I said, start with 1, and you know how to count from elementary school, right? So yes, go ahead. The vector that will encode the positional information. So this is what the whole discussion is about. This is the original kind of vector. Encode the positional information is actually here, results into this vector with addition. This simple way of concatenation of this positional information, 1, 2, 3, and so on, definitely is not the best thing, because by concatenation, we're also increasing the number of dimensions. So we are paying some cost. And this is also does not scale. Okay, so they prefer to actually engage into a method that adds a perturbation, if you think about it, to the original kind of vector x. This perturbation is this kind of R vector, which they manage to make it not to have some really introduce huge offsets from the original location of the x vector. So we need to be managing that, right? So we'll see how that will be managed. So come on, you can't do it. It always switches off. Okay, so these guys defined a completely incomprehensible set of equations. RIN. This is the I is the index of the token, and n is the nth element of the R vector, state the obvious, okay, is equal to sinus I divided by capital T n divided by D, where n is even, and cosinus I divided by E to the power of n minus 1 divided by D when n is equal to odd. And T is the context size as we already have seen it. And if you plot these functions, which I will attempt to plot in a very scientific way, as you will see, there is going to be some plot like this. For the plot, for the actual plot, you can go to the original paper. If I remember right, it's there, the actual plot. But the explanation here that I'm bringing here is from the latest book of Bishop. Okay. This is the only explanation I found to be a reasonable one. That's why I'm actually bringing it here. The actual plot is there. But I will try to approximate as much as possible. So over here I have D, the dimensionality of the dimensionality of the vector of the embedding space, if you like, and this is my T. This is my T. This is my context, and of course, the position inside the context is obviously an integer number, right? So if I plot the function, so I have, for example, here the R1. The first element, the second element, the third element, and so on and so on and so on, all the way to the RD element, right, of the vector. So the first is going to be a very high frequency waveform like this, sinusoidal, obviously, waveform. I'm not expecting any miracles here, just a sinusoidal waveform with some frequency. Then will be the next, if I plot the R2, RI2, right? The RI2, right? So I'm going to get another sinusoid. As you can see, the diagram is scientific, so it's very accurate. So and then if I progress, right, I will see 1 octave smaller frequency as I'm progressing. And so the question is, what on earth is going on here? I mean, then they said, if you are to encode the fact that you're in 3 position, draw a straight line and read the values of your vector R, R1, R2, R3, R4, all the way to R8. Let's assume D is equal to 8. Okay. And add it to the vector X, and then trust that it will work. Okay, so then Bishop said, okay, fine, okay. What if I want to think about this way? I want to think about this position 3 or whatever as a decimal number. I want to convert this into a binary number, right? So I'm going to obviously start with the first position. So I have some columns over here. Okay, so it will be 0, 0, 0, 0, 0, 0, 1. Second position, 0, 0, 0, 0, 0, 1, 0. Third position. What is this? 1, 1. Correct? Then yes, I know how to do the binary to decimal conversion. However, I want to draw your attention. Oh, this is not this is a 0. I want to draw your attention to the last column. Isn't this the highest frequency? In the digital domain, it's highest frequency. Square waves, 0, 1, 0, 1, 0, 1, 0, 1. Then we have 0, 1, 1, 0, 0, 1, 1, 0, 0, 1 octave molar. If you complete this kind of matrix, you will form in the digital equivalent of this guy. Another question became, what is the bias at the end of the day? And the reason why we are suspecting, including Bishop, that this thing is adopted is the fact that the cosinus and sinus kind of terms are functions between -1 and +1, right? But on average, they are close to 0, right? So the offsets that they are causing in the original kind of vectors are minimal. Still encoding the information, but with minimal offsets. So that's the explanation of the original kind of paper in terms of positional encodings. Okay. So this is another time where I want to mention where to go next, okay? Because I didn't have time to go through over here some engineering kind of aspects of how to use the transformers, for example, to, well, okay, you can train or you can fine tune, you can do certain things with them, language models. And I don't have any Python code in the website for a reason where there's one book in particular, which I kind of like, not because it goes through the why questions, why the architecture is the, we tried here to go through the why questions with some intuition. But definitely this book takes you through the implementation of a language model from scratch. Okay? So the first kind of chapters are on the transformer kind of architecture. If I show the chapters, this book is called Build a Large Language Model from Scratch. So the Python code is there for all the blocks that we have gone through today. Obviously, the book is free of charge available to you. So if I were you, I would definitely, not for the exam again, for the exam is sufficient, your notes will be sufficient. But for after the exam, to actually go through some of these kind of chapters. Now, at some point, the architectural discussion is done, the transformer is formed, and the author starts to deal with some interesting things, like, for example, in chapter 7, which is the usage part, right? What are the use cases? Fine-tuning to follow instructions. And because the implementation is from scratch, then you understand how to do the fine-tuning, which most of the time you will do fine-tuning. Most of the time in your life you will do fine-tuning, unless you are, of course, I wish you the best of luck to be associated with core teams which are doing training, right? And at the level where it is interesting. Of course, there are many people are doing training, but sometimes the jobs are like monitoring, data stuff, whatever. Okay, so this is basically one of the books. The other book, which is very popular, is the engineering aspects of learning, not about the actual fine-tuning and the principal kind of ways, LoRa, all this kind of stuff, the sort of techniques, but the engineering aspect, that's AI ops, okay? The AI operations. And this book is, I don't have it here handy, I don't want to spend time on that. I will post these two books on the Discord tomorrow at some point. Okay. I'm forgetting, AI engineering is the title of the other book. I think many of you know it already, AI engineering. And this goes through the engineering discussions. Of course, to do engineering, you need to have a lot of GPUs, but at least you can read it and understand all the issues associated with engineering. Okay, and with that said, I am going now to attempt in the last 20 minutes to actually go into the discussion of the last representation we're going to discuss in this course, which is symbolic representation. The remaining lectures will be associated with optimal control, optimal sequential decision making, that is. And thus, this representation is going to allow us to build rule-based systems, or in many use cases, are combined with neural representations to form to help in two tasks. One is how can we make large language models potentially more deterministic by imposing certain constraints into them. Obviously, the determinism here today is attempted via a variety of tools that our agents are actually calling, either because we impose a determinism because, oh, when you finish this task, call this hook to do this, right? Sometimes they follow it, sometimes they don't follow it. Or logical reasoning is also used in other domains as well outside of LLMs, like in cybersecurity, and I'll show you a couple of use cases that AWS is using them to on that kind of domain. Okay, so I'm going to just do that for 20 minutes, and I'll continue next time. Notes. I hope the website is ready for this discussion. Here is a reasoning chapter. I checked. The same author, by the way, who wrote this large language models from scratch, has a subsequent title that talks about LLM reasoning, chain of thoughts, things of that nature, which now that I'm thinking about it, the whole discussion that we leave on the table is like worthy of a course, a complete course. Is there any course like this in NYU today? No. Okay. So first, the use case. What happened to the? Anyway, there was a video. So AWS started hiring logicians several years ago, and the reason why they were hiring them is they did the following. They took the whole. There's a proprietary language in AWS or in many cloud providers called the cloud formation. Anyone heard about cloud formation? Yeah, okay. So they took the cloud formation, which basically, I may be wrong about the language. In many years that I have not touched AWS after receiving an $8,000 bill from them. But the cloud formation is the language which specifies the infrastructure. Is that the cloud formation language specifies the infrastructure? Yes. Okay. So they have, let's say, a server there, 150 containers here, there, whatever. So there is they took this kind of as input and they converted it to logical statements. Okay? When the whole infrastructure was converted to logical statements in a knowledge base, in other words, then they were able to ask questions such as, who has access to this? Is this person has access to that specific endpoint? Is this container accessible from the internet? So it's straightforward if you have, let's say, 100 servers, 200 servers maybe, and things like that. But when you're running 1 million containers, as many enterprises are actually running, like coming up and down, then the questions become definitely non-trivial, right? So there was, one upon a time, a video on that website. I'll bring it up tomorrow or during the weekend to watch from the presentation of AWS on the sort of theoretical foundations of that work and how it led to. So right now they have the largest logical reasoning engine deployment in the world. right? Because of that, you can actually use it as part of your AWS deployments. But in any case, I want to start from a much more mundane, sort of topics, which is what we're trying to do with logical reasoning. First of all, if I am to draw something, I will draw two boxes, and one of them is going to be associated with syntax, and the other part of the discussion is associated with semantics. So with the syntax, we are going to be concerned with how to represent a sentence, a rule, in other words. And with semantics is we are going to be building word models, as we call them. Nothing to do with the Smith-Huber word models. It's a completely different animal. And this is part of another course that I'm teaching. But word models, it's going to be limited to the specific things that I'm going to mention. We are going to definitely use semantics to evaluate those models. And also in terms of inference. So inference is going to be as touch points in both the semantics and in the syntax. In other words, we will learn a method to do inference using just semantics, and also, like at a later point, using the word models, and then do inference logical reasoning, in other words, using just syntax alone. And it is really that method that AWS is using, right? It is really the second method. It was called theorem proving. Probably you've done some discrete math in the past. Did you? Yeah. So some of that probably will be familiar. And one other thing that we are going to always work with is a knowledge base. So I am going to start with syntax. So we are going to be using a language that consists of propositional symbols, which of course symbols that evaluate whether true or false, and operators, which is obviously many. There is the negation, there is conjunction, there is disjunction, there is implication, and there is double implication. I'm sure you're familiar with some of these operators. Just to give you an idea about building, if you like, some kind of primitive sentences. Obviously, we have a sentence, let's say, I'm going to use these letters, alpha, let's say 1, let's say rain, and wet. And obviously, there is two variables involved here because both are propositional kind of variables. So both variables are, the sentence is satisfied by when the value, truth value of each variable is the one shaded. Okay, then this satisfies the sentence, obviously. So we call this number of this model of the word that satisfies a sentence. And we will denoted with small letter m. We are, in many instances, going to be dealing with many models that can potentially satisfy sentence, not only one, right? But in another example, which is actually trivial, which I'm not going to, if I had an or, for example, rain or snow, then you can understand that there are, I'm not going to expand on that. That's kind of trivial. There are many models that satisfy this sentence, 3 in this case. So we'll be using, just for the notation, this capital M to indicate that the set of models that satisfy the sentence. So it's M1, M2, M3. So this is M1, M2, M3. So this is a notation I wanted to use, small letter m and capital kind of thing. So now, obviously, we are going to have a set of rules that we are all familiar with, like what is a conjunction, what is a negation, what is disjunction. Everyone is familiar with these kind of rules. There's this implication kind of rule that causes sometimes some confusion with respect to its truth table. And I have some kind of a limited kind of treatment on this implication rule just to understand it a little bit more, because we are going to use it. So the implication rule, if you remember, has this table. So it has the P, Q, and then there is the implication and the double implication. So P, Q, P implies Q, and P double implication Q. Okay, so there are 4 possible values here. So obviously we have false, false. What is the implication? Anyone remember from? So this is true, and this is true. False, true. This is true, and this is false. True, false. False, false. True, true. True, true. That's basically the I will call it cases 1, 2, 3, 4. And so when you're dealing with, let's say, with this kind of a sentence, it's actually always a good idea to try to convey or to have some kind of example in English to understand, why on earth when we have F implies false, the implication rule is true, for example. So I have here some set of sentences. For example, if it is not raining, it cannot be cloudy. And this is obviously true. The second example that I have is that if it is not raining, it can't be cloudy. And this is obviously true. And for 3, if it is raining, it cannot be cloudy. And this is obviously false. And 4, finally, if it is raining, it can't be cloudy. And this is obviously true. And if you kind of believe that's kind of behavior of this implication rule, then the double implication is kind of straightforward from what we will use as equivalencies. So this is obviously P implies Q and Q implies P. And if you know the truth table of the conjunction here, then the truth table of the double implication is immediately available to us. So this is just in passing, in case someone was kind of confused by this kind of truth table. So for every operator, we're going to have truth tables, and this is one of them. So what we will do now, unfortunately not right now, but what I'm going to do next time is I'll tell you the trajectory here in kind of logical reasoning. I'm going to introduce the logical reasoning in two stages. The first is I'm going to introduce a game. This game was several kind of decades old, and became sort of the game with an agent who is trying to find a goal and exit the game. Obviously, there are some kind of dangers around. There is a monster, there is a glitch, and so on. And also, there's some kind of sensing. So there's some kind of perceptive information this agent is receiving, making decisions very conservatively as it will move around this kind of small world. And every step that it makes, it has to make a reasoning step as to whether this cell is safe to go or not. Otherwise, it doesn't move. Very conservative. So we'll do this exercise of finding the goal next time using this approach. But instead of logical inference, we will use inference with our heads, right, to see, okay, is it safe? Then we will start writing down the rules in the knowledge base. And then we will see an algorithm that is going to be able to do the logical reasoning for us. And after we see this algorithm, this is basically going to finish the semantic method of inference or logical inference, where the world models are going to be used in order to do the logical inferences. Finally, and I'm not expecting to last for more than 1 hour, this whole discussion, because I want to move to the next kind of topic. Finally, we will use syntax only and theorem proving to do the same thing. So we will use just the syntax in the knowledge base and some other lookup tables which I will introduce to actually drive the logical reasoning. Okay? And then that will be the end discussion. It's a short discussion on logical reasoning. However, probably you will get something associated with propositional logic. And how do you apply it in the future? Unfortunately, I'm not covering. Yes, go ahead.
When you say world models, do you mean like, what do you mean?
Not the Smith-Huber world models. No, said that. No, that's not the case. This is just world models like, as we will see, a world model is this model where there's a whole bunch of rules that are going to the knowledge base, and as the agent moves around, more and more rules are being added to the knowledge base as the time goes by. And then we will see how the logical constraints are resolved to do logical reasoning. All right, so a little bit thin on the application space other than this game, but it is part of the syllabus, and hopefully you may build or request to be built some kind of a rule-based system in the future. The rule-based systems are widespread even today, and for mission-critical industry, so some of this knowledge is okay to have. But will not occupy next week more than, that's my target, more than 1 hour. Then I'll go and finish the discussion next week with, as I said, planning and task planning, the planning description, domain description language. And this will finish the lecture, and then the remaining two, as I said, MDP and reinforcement learning, if I have the time to complete both. Okay. All right, thank you.